Alright, so here's a second video for conservation of energy, where we're going to go over this example where we combine conservation of energy and using it along with conservation of momentum. So we have a 15-gram bullet shot into a 3-kilogram block of wood, and it's hanging on a string, and the block of wood with the bullet in it rises up. This is called a ballistic pendulum, and if you click on that link that's popped up over ballistic pendulum, you can see one in action, and just to get a visual of what we're dealing with here. We're trying to find the speed of that bullet. To do that, so we've got all of our giddens, we actually have to break this up into two steps. The part after the collision, and then like only after the collision when the block and the bullet are together, and then the part around the collision where the bullet it's on its own and then hits the block. So we have to look at it in 2 points in time. So the first part is looking at it when it's all together and it's moving and it's going up along the pendulum, rising up to a maximum height, which is a transfer of energy from kinetic to potential. And so doing that, we have to use conservation of energy. So we have Eg plus Ek is equal to Eg prime plus Ek prime. Now all we're told is that it gets 17 centimeters higher. So the best thing to do is to say that our reference point is when it's at its lowest point. So that would make our initial potential 0. And if it goes up to a maximum height of 17 centimeters, that means at that point it momentarily stopped, which means that its kinetic energy at that point is 0. And so we actually end up with a slightly, a little bit simpler equation, but what we have to do is use it to figure out the speed. So write out that 1/2 mv squared, and this v that we're looking for is the speed of the block and bullet after they've been colliding but before they start rising. And then we're going to have it transferred into mgh. Now this mass, because it's both, is going to be the mass total. And so here we are, now we have to rearrange, we're looking for speed. The mass is actually in both terms, so if we divided it, it's going to cancel out. So the mass cancels out in this equation, and we get left with 2gh all square rooted. That's, nice convenient calculation. And that's going to give us, with a few extra sig figs, it's always good to keep these for later because we're using this number. It's not our final answer. That and how many sig figs it would have 2, so I'll just put a little mark underneath there. Now for step 2, our end goal is to get the speed of the bullet. The bullet hits the block, so there's a collision there. What do we know about collisions? Momentum is conserved, no matter what type of collision it is. We know it is an inelastic collision because the two objects stick together after they collide. So we have to go to conservation of momentum. We're looking for the speed of the bullet before the collision, and we just figured out the speed of the block and the bullet after the collision. That's what we just calculated. So we have, hopefully, all that we need. So if we're thinking about this, we're going to have the speed of momentum of the bullet plus the initial momentum of the block is equal to the momentum of the bullet block afterwards, because it's, they're all one, so they have the same speed and it can have a total mass. Now the block is not moving, it's just hanging there, so this is actually 0. So this, again, simplifying our calculations a little bit. So we've got the mass of the bullet times the velocity. It's a vector for momentum, but we're just dealing with magnitudes here, so we can drop the vector arrow now. And then the speed of that bullet beforehand, so VB0, is equal to the mass total, bullet plus the block, times V. Now that V we just calculated. So we can easily rearrange this. VB0 is equal to the total mass times the speed over the mass of the bullet, which is going to be So we have 3.000 kilograms plus 0.015 kilograms times 1.8254 meters per second, all over 0.015 kilograms. And that gives us a speed of the bullet initially of 370, not 367, 370 meters per second. Your calculator would get 366.9 approximately, which to 2 sig figs, our final answer is 370. So that's how you can use momentum and energy in the same question to solve for an unknown value. These are very typical type questions to see on an exam because they involve two very big ideas. We will be investigating collisions next and how that will work into our conservation laws again. So this is a really good example type question, and there's going to be lots more of these in the homework, which you see there. So make sure that you do try and test that. Always, when you're getting answers, make sure they're realistic. 370 meters per second is really fast. That's faster than the speed of sound. But if you think about the speed of a bullet, bullets do easily break the speed of sound. And so that is a realistic answer for this question, but it wouldn't be a realistic answer for every question. So always keep that check in mind. And as always, physics is awesome.